All right. So let's continue with this example, which tests two proportions, populations proportions. It's a two sample z-test for proportions. So here, a quality inspector finds 10 defective parts in a sample of 500 parts received from manufacturer A. So we are going to be comparing two manufacturers, manufacturer A and manufacturer B. And in one, we get a sample of size 500. In the other, we get a sample of size 400. And the number of defective parts are given as 10 and 12, respectively. And a computer making company uses these parts in their computers and claims that the quality of the parts produced by A and B is the same. So whether we have more defective ones. So it's interesting. So this is a smaller sample, 400. Okay. Out of four, yeah. In B, manufacturer B, 12 are defective out of 400. So more defective from a smaller sample size. And this is 500, 10 defective out of 500, but they claim that they're the same. Are they the same or are they really different from each other? So this is what we want to claim. So at 5% level of significance, do you have enough evidence to disprove this claim? Your claim may be here, you may still be, for example, assuming that, as you can see, manufacturer B has more defective ones in a smaller sample size. So you may actually be still looking at evidence against B, where your alternative hypothesis is PB greater than PA, or PA smaller than PB. So you may have a left or right tail, depending on which how you put this. You may have, so it's PA minus PB. So you may have actually it's left tail hypothesis, assuming that PA less than PB. Okay, so you may expect if this PB is going to be much larger, that's your extreme case. In this case, you will have a left tail alternative hypothesis. But that's really, in this example, for example, we had just left it like that because in the question does not say that B is, can you have evidence that B is really worse in terms of defective parts compared to A? It doesn't say that. It just say, are they the same or are they different? So in that case, we may assume both extreme cases, whether B is smaller or A is smaller, has smaller proportion of defective elements, both of them you can accept evidences, but it's not going to be incorrect by just looking at this intuitively. Oh, okay, B's proportion is larger, so I'm going to be looking at an evidence whether this proportion being larger is significant or not. So you can have a left tail test for that too. Okay, that will not be wrong. Now, the only difference having a left tail and right tail test in this case will be that alpha that you have here, which is 0.05, with a 5% level of significance, 0.05, you would be either, it will change your alpha if you conduct a two-tail test. It will, on the right hand part, it will be it will be 2.5% one side, 2.5% on the other side. So it will be like decreasing your level of significance if the difference between two-tail and one-tail test, because we already know that PB is larger than PA, so it's going to be some negative value here. But yeah, depending on whether this negativity, are you looking for this, whether this negativity is extreme or do you accept something positive here too? Okay, so we don't expect anything positive here, but so what I'm saying is that both alternatives could be done here, and you have to write that in your assumption. So this is basically the author's justification that this is a two-sided test, is because there is no direction of the alternative has been indicated. So if in the question it says that does the manufacturer B really worse than manufacturer A, it doesn't say in the question. Okay, it just say they have the same. So since there's no direction indicated in the question specifically, you may claim that it's a two-tailed test. Okay, but you may also have a justification here saying that it's obvious that part manufacturer B has a larger proportion of defective ones, so it will be good to test whether B is worse than A. So that's why I have a one-tailed t-test, a one-tailed z-test. That's also possible. I think both justifications are valid justifications, and they can all be accepted as correct. Now, so we first have the test statistic. The proportion, as you can see, 0.02 from sample 1 and 0.03, as we intuitively figured out. A smaller sample size, larger defective numbers is 0.03. So this difference is like 50% more than what this one has actually. 0.02, 2% defective parts, 3% defective part, 1% unit larger. And here the tested value is d is equal to 0. So our null hypothesis is that they are equal. Okay, so in the assumption that they're equal, so if they were 0 here and they're equal, we will have a z value 0. Okay, if we got here, if they were really equal, if we will get 0 here as the z value 0 divided by whatever standard error is, we will get 0, and they will be indeed equal. But there's a difference of 0.01 minus 0.01 here, and what we do here, we don't have any assumptions as to population variance, so we compute the variance of both populations separately. So as this is Bernoulli data, the variance depends on the unknown parameters PA and PV, which are estimated from these samples, and we don't assume equality of these proportions. Actually, our null hypothesis was they're equal. Okay, so we could have conducted pooled variance here too. So this is one way to do that. An alternative would be, since our null hypothesis is already assuming that these are equal to each other, okay, then why don't we compute a pooled variance by computing a single p? And that's also, we can do that. I think at the rest of the example, it's doing that in a separate section. But it's also possible, as I said, because our assumption, null hypothesis assumption, is that they are equal. So let's assume equality of those variances as well. This is the variance of that manufacturer A's and the sample size. So this is our standard error. So when we divide the difference with the standard error, this is what we get. And our acceptance and rejections region are 1.96 in both sides, from minus 1.96 plus 1.96, and this is within the limits. Okay, so this is within that minus 1.6 and plus 1.6, so it's in the acceptance region. So although there is difference between their proportions with this significance level, we say that the sample that we collected does not provide sufficient evidence that they are different. So we may accept that they are the same. Okay, so although they are unequal, although one of them is 0.02, the other is 0.03, with this level of significance, 0.05, this evidence is not sufficient enough to claim that they are different. So we cannot accept the alternative. We have to accept the null hypothesis, because this z value is inside that region of acceptance. So we could have, for the same example, as I said, we could have, so this is the example 9.26 continued. We could have computed the pooled proportion to compute the pooled variance by putting all those number of defective ones and the total sample size together, and this becomes our pooled variance. And as you can see, it didn't make too much difference. Here it was minus 0.945, this is minus 0.966. It's still within the acceptance region. So having a pooled one or individual variances did not do anything. If our null hypothesis says that they're different. For example, our null hypothesis could be in the case that they're not different, but the null hypothesis would be in such a way that the difference between them is at least 5%. So it has to, this D again has to be some fixed value. Null hypothesis cannot just say they're different. Null hypothesis would be like the defective parts in manufacturer B is at least 5% points larger than the other one. Okay, so in that case, D is going to be, so the difference between them is 0.05. So we are going to look at this difference and minus 0.05, and we are going to take a look at that difference. And since if we assume that they're different, we would not be able to use pooled standard error in that case. We had to compute them like this by assuming, by using the sample variances here directly. And this D would have to be something specific. We cannot have a null hypothesis just claiming that they're different. Okay, so in that case, you have to form your hypothesis that they are same, and then if you can show that they are different, you will be showing that they are different. So difference and same, always that sameness will be your null hypothesis. You cannot just have a null hypothesis saying that they are different. You have to specify how much different they are. Null hypothesis always have to be very specific. I think we have an example on that too. Let's take a look at that. We have a proportion. So the t-test, when we have unknown variance, when we don't know the population standard deviation, we estimate it, and the resulting t-statistic. This doesn't talk about whether the sample size is small or large at all, but as I said, when sample size is large, t-test is no longer different than the z-test. When you have 120 samples, even more than 30, you'll see that the t-values you're going to get here are going to be very similar to. So these t-alpha values will be very similar to z-alpha values for large values of data points for large sample sizes. So let's try to look at the difference between population. This is still the mean. I think there was something about some elections, some example. Let me see. This is not that one. Yeah, pre-election poll. Oh, this is actually just about the duality of confidence intervals. So let me take a find an example. Maybe it's with this p-value. Not here. Do we have? Maybe I can just take a look at an exercise at the end. This is still the means quality inspection. This is the p-value. Yeah, let's take it. Oh, by the way, we're not going to talk about 9.5. We will finish this chapter 9 at the end of 9.4. This is not included. We're not going to cover inferences about variances. So let me go at the end of the chapter exercises to see whether we have an example about proportions, where difference between proportions, where we have some difference between them. I'll quickly, so this is normal shipments. This is not that one. Yeah, I think this may be such an example. Two candidates, so it's about proportions. So 9.17, I can understand it's about proportions. So these are about the margin of errors. So this is about confidence interval. It's not that. So, and this is about those variances. Yeah, I couldn't find such an example, but yeah, the we have a claim that the two proportions are different from each other, and in that case we would have to specify in our null hypothesis how different, exactly how different those two proportions are by specifying a fixed value. Now, at the next section, subsection, we are going to talk about the equality of two-tail hypothesis test with confidence intervals. Okay, so this duality, a two-sided test and a two-sided confidence interval, is basically the same thing actually. When we conduct a level alpha z test in which the hypothesis is this, we are testing some parameter equality, and we have a two-tail test where we're just looking at the difference. It will accept the null hypothesis only if we build a confidence interval for this, and if our theta 0 that we have here in our hypothesis, if it is inside the confidence interval that we build, then that's the same thing actually. So it's really interesting here. When we were in our z-test, so this is the test statistic in the z-test, where we have this theta 0 inside our standard z value, right? Now, but when we are computing a confidence interval, we are computing a confidence interval around theta hat. So this theta 0 actually is not here when we are building a confidence interval. Okay, actually it is, yeah, we just have this theta, we standardize it with its expected value, and this expected value is, if it's unbiased, it will be actually, we will use our null distributions theta 0 value for this. So this is basically saying that unstandardizing it is the same as, these two equations are the same, and this refers to our confidence interval. If you look at this, the right-hand side is our margin, and this interval that we build around is, this is theta 0 is at the center. So we conduct a two-sided test, assuming that theta is theta 0. Whenever the confidence interval around theta, here this theta is going to, theta hat is going to be our center. It's not actually, theta hat is our center. So theta 0 here is not part of the confidence interval. If you, what I mean is this. Let me take a, let me just draw it here. Not open. I have to say new. So we build a symmetric confidence interval around theta hat. For example, x bar. Let's have a new one. So how we build a confidence interval is we have our x bar, and we, based on the z value we have, we compute a confidence interval around x bar. X bar is at the center, not x square. X bar is at the center here, and this is our margin. Okay, minus the delta is our margin here. So this is basically saying that when we're building this x bar around this, we just have our z alpha. When we are computing this x bar and this margin, we only have the standard error of x bar multiplied by this z alpha value. So we go, our margin is standard error of this by z alpha. So as you can see in our confidence interval, this mu is nowhere to be seen. But we say that mu contain mu, this interval contains mu with 1 over alpha probability. This is how we built the confidence interval. Mu may be here, it may be here. It's not centered around mu. But this is saying that whatever your x bar is, this probability of 1 minus mu being in this interval with 1 minus alpha probability is the same as x bar being in mu's, if null distribution was correct, if we build a confidence interval around it, x bar being contained in an interval of certain size when we unstandardize it. This is they are dual things, and the duality comes from the fact that you just this was your margin, we see that the distance from theta 0 to the center of the z interval does not exceed this margin. So so this one also is showing that. So this is a hypothesis test, which is two-sided, and this is our confidence interval. Okay, the probability that theta 0 is contained in this interval is the same as this z being here in this region. So those two probabilities are equal to each other. So which means that you may just build a confidence interval around your z as usual and see whether your null hypothesis value mu0. If mu0 is in that interval, you accept that null hypothesis. If not, you reject the hypothesis. So let's take a look at some examples, this pre-election poll or this hardware upgrades. Or these are all previous examples that we did in for building confidence interval. And let's try to, these examples try to convert them to hypothesis tests. For example, the effectiveness of the hardware upgrade. There was a 90% confidence interval. By the way, this duality is correct only when we conduct two-tail hypothesis. Okay, so one-tail test does not really has duality with confidence interval. So when we conduct a two-tail hypothesis test, only if you're interested, our alternative is just not equality like this, then we can build the confidence interval and see whether that is inside this confidence, our mu0 is in this interval or not. So with 90% confidence interval, the difference between mu x, mu y in the mean running times was 0.7 and 1.9. Okay, so this is at 90% confidence. So if we claim that, if our hypothesis is that these two mean they are equal, okay, our null hypothesis will be this: mu x is equal to mu y, and or mu x minus mu y is equal to 0. And since this 0 is not contained in this interval, we would reject null hypothesis in favor of reject this hypothesis in favor of the alternative hypothesis, saying that the upgrade is indeed successful, or this the sample that we observe provides sufficient evidence at 10% level of significance. The null hypothesis should be rejected, okay, in favor of the alternative hypothesis. Now, actually, this may also provide a good example for an hypothesis. What if you say that we don't want to claim that they're equal, but we want to claim that they are different and they're this much different? For example, the difference between them, the difference between their means is 0.8, okay? I may claim that the difference between their means is 0.8, and that may be my null hypothesis, okay? The difference between, I may claim that mu x minus mu y is 0.8. In this case, I may conduct my null hypothesis. So null hypothesis is like your claim, okay? Now, in this case, the alternative would be if the collected evidence provides, the collected sample provides evidence significant enough that it's less than 0.8, the differences between less than 0.8 or more than 0.8, significant difference that it's not 0.8, then we will say that you cannot assume that null hypothesis. So what we will be doing is that when you say mu x minus mu y is equal to 0.8 here, what you will be doing is when you're computing this test statistic here, you will be computing test statistic also using that 0.8 into account. Yeah, now if your confidence interval will not change in that case, okay, because you're claiming that the difference is that, and that difference that you're claiming is indeed in this confidence interval. 0.8 is in this interval, so null hypothesis can be accepted in that case. So when we say that the difference between these two mean values is 0.8, there is no evidence suggesting that it is less than that, significant evidence suggesting that the difference is less than 0.8 or larger than 0.8. So if the observed difference and if the confidence interval that you built around the observed difference did not include that 0.8 here, you would say that you cannot just claim that null hypothesis is probably the other way around. Okay, so this is that we may have a null hypothesis with a specific difference value in our question. And the last thing we're going to talk about in this section is the concept of p-value, which actually is raised by this first question. How do we choose alpha in the first place? How do you say I want to conduct a z-test with alpha is equal to 0.05 or alpha is equal to 0.01? Sometimes a certain choice of alpha may be very critical. For example, what if you compute the z-value, which is, for this alpha, 0.05, when you conduct a two-tailed test, it's 1.96, right? So z alpha over 2 was 1.96 when alpha is equal to 0.05. What if you compute a z-value based on a sample and it turns out to be 2.01? In this case, it's in the rejection region, and reject the null hypothesis, reject H0. But as you can see, 2.01 is really very close to 1.96. So if we had, instead of using 0.05 as our significance level, maybe if we had chosen alpha is equal to 0.04 or alpha is equal to 0.01, this z 2.01 would probably be in the acceptance region. So the specific choice of alpha is really important. In one case we are saying accept H0, in the other case we say reject H0, which are binary decisions that we make at the end, okay? Depending on whether the z is inside the rejection region or not. Now, it is inside the rejection region. As you can see, 2.01 is larger than 1.96 when alpha is 0.05. We reject the null hypothesis. But when you make alpha is equal to when you have your significance level, or when you increase your confidence to 96% or 97%, the z alpha over 2 in this case may be 2.04. When it's 2.04, your z value is 2.04. Now this time this 2.01 that you collect from your sample is now in the acceptance region. So you accept and reject your null hypothesis easily based on a small change in alpha value. This is bad, right? In certain situations, when the z value is close to this other value, which we call such cases as a too close to call situations. When the z value that we compute was like 8, 7, it's really large. There is no this, which means that this evidence is really strong enough. It's very strong that this should be rejected. Null hypothesis should be rejected. Or z value may be too small that when you compute a z value, it's 0.01 or 0. Like if you have a z value that you compute, it's something small like 0.2. It's very close to 0. Again, even if you have a low confidence, you will still accept the null hypothesis. So here, the concept of p-value is, instead of fixing a fixed alpha like this, why don't we compute the alpha value that corresponds directly to this observed z value? So this was 2.01, right? At which threshold? So just imagine we have a lever, alpha lever, which we can slide over the z-axis, and whatever z value we compute here. So I'm trying to do this. So if we had fixed alphas, that acceptance, so these are some fixed alphas. Imagine these are fixed alpha values. When we had them, if our z value is here, we are rejecting the null hypothesis. And when the z value is here, we are accepting the null hypothesis. And these two z values may be close to each other, actually. Now, what if we have an alpha? What if alpha, instead of having alpha this, if we move alpha to this side, when alpha becomes exactly at this value, when z alpha is exactly coinciding on the second z value, and this is the first v value, this is like a threshold where when alpha is smaller than this, we are going to accept this alpha, and larger than this, we are going to reject this null hypothesis for this z value. So this, the threshold value of alpha that puts a boundary between acceptance and rejection region is actually called the p-value. P-value is a really intuitive meaning. Actually, the way that is described like this, which is the threshold between acceptance and rejection, is not so intuitive. Actually, p-value is simply, you have a sample, you observe something for your sample, x bar. What is the probability that is coming from the null distribution? What is the probability that a random sample coming from the null distribution has more extreme values than your x bar? That probability, which is the area under the curve to the right hand side, is called the p-value. It's like this. You're saying that I found something. This is my sample. I found it. Or I believe that it's extreme. And we just ask, how extreme is your sample really? What is the probability that a random sample, a random point from the null distribution has a more equal to or more extreme value than what you have computed? That's the area under the curve to the right hand side. That's the p-value that we want. And if the alpha value, by the way, this p-value is of concern only we have one tail tests, okay? So we will be looking for in one extreme. Your z value, if it's somewhere here at the center, it will never be extreme. So for a sample that we collect, we are going to compute a z value. It may be either on this side of the tail or on this side of the tail, but when we're asking that how extreme is this observation, we will be asking this question: what is the probability of obtaining same or more extreme observation from the null distribution? This is the area to the curve to the left hand side of this z. If your z was a positive number, it will be the area under the curve to the right hand side of this. So this is the probability that a random sample from H0 is more extreme than your sample. So that's what we call, I mean, in other words, if the alpha value that we have chosen was exactly produce this z value that you have from your sample, that will be the threshold. So this p-value tells us this threshold, and the rule of thumb is that if this p-value that you get is a small number like 0.01, smaller than 0.05, the most widely used threshold for a p-value is 0.05. If the p-value you compute for a z is less than or equal to 0.05, you mean that it's extreme enough, it's a significant enough case. Smaller values of p-value means that your sample is significantly different than this one. All right, so that's the discussion of p-value basically. So then that's the last slide here on this chapter 9. So as I said, this is the observed size of effect. This is our observed z samples z value, and p-value is the area under the curve to the right hand side of this. If it falls on this tail. If your observed effect is to the left hand side here, p-value will be the area under the curve to the left. And this is our null hypothesis. In the last couple of minutes, actually, I may give a better example on the p-value, the concept of p-value, which is something like this. Imagine you have an algorithm. So I give this example in my introduction to bioinformatics class. So if you're also taking that class, you already know this example. So imagine we have an algorithm, okay, and we claim that our algorithm finds some good results, something from a graph. So imagine we have an algorithm that works on a graph, on large graphs, and from these large but sparse graphs, imagine we have a very large, tens of thousands of nodes, maybe millions of edges, a graph which has many vertices and many edges. And imagine we have an algorithm which finds subgraphs from this graph which are dense. So like communities. This is in graph theory or in graph algorithms, this is called community detection. Uh, so our goal is like, this may be like a Facebook social network graph, and our goal will be to find a group of people who know each other, lots of edges in between them. The extreme case of the problem where we try to find a community in which everybody knows everybody, and finding the largest of such community in that graph is called the maximum clique problem, which is NP complete. So nobody has found an efficient solution to this problem yet. But we relax that problem a little bit. We're not looking for cliques, complete subgraphs, but we're looking for dense subgraphs, which means that the overall original graph is not that dense. It's very sparse, like the Facebook graph. I mean, how many friends on the average everybody has on Facebook? 1,000, 2,000, 10,000? Compare the value of 10,000 to the value to the size of the vertices, which is probably like 1 billion. If there are 1 billion users on Facebook, out of 1 billion, you're connected to only 10,000 of them on the average, which means that almost a billion of those edges are missing. So it's a very sparse graph. But you may find a community of people in which a lot of people know. You may find a dense subcomponent. So imagine we have an algorithm which we claim finds a dense subgraph, and such a dense subgraph actually is some extreme case. If our our goal is to find a dense subgraph as large as possible. Okay, I mean, in a trivial case, for example, you may say, oh, okay, I have found a very dense subgraph. It's densest. It contains just 2 nodes, a single edge. Okay, 2 nodes and a single edge is a very dense graph. Its density is 1.0. It's very dense, but it just contains 2 nodes. Okay, so it's not significant. So there are 2 competing measures again here in this dense subgraph. We want to have as large as much number of nodes, as many number of nodes as possible. But putting more nodes make it less dense. So these are 2 competing measures. And imagine we have an algorithm which can find dense and large subgraphs. Now, how do we measure the effectiveness of our algorithm? If some algorithm says, okay, I have found this graph as the dense graph, how good that is. If somebody else comes, oh, I have found another graph, its size is this, and I claim my result is better than yours. Which result is better? How do we compare them? What we do is we compare how different is this dense graph from some null distribution, how extreme this subgraph that the algorithm has found. So what do? We, for example, first form ourselves a null distribution, which will probably not be normal, which we compute some numerical value for a subgraph. We collect random subgraphs. For example, our null distribution in this case is that having a dumb algorithm, a baseline, saying that just select random subsets of nodes from this original graph. For example, if I have found a subgraph of size n, and this one has found subgraph of size m, what if we form our null distribution by selecting random subsets of size n from this entire graph and compute something about them? For example, how many edges that those random subgraphs have. And this null distribution in this case may show, it may be an histogram showing how many edges, it may show how many edges that random one has. And if your algorithm is extreme, it will fall somewhere here, okay? The probability that a random graph have more edges than what your algorithm has found will be the area under the curve here. So it will be the p-value of your algorithm. So what we can do is we can compare the p-value for both of these graphs by comparing them against their null distributions, because this null distribution will have to be computed differently for each different size of subgraph size, right? I mean, for 3-node subgraphs, the number of edges a 3-node subgraph contains is going to be different than the number of edges a 5-node or 20-node subgraph has. So we will conduct an H0 for example, 20-node subgraphs. Our null distribution will be the entire population, sampled from the entire population. Just take random 20-node subgraphs. See how many edges they have. If your algorithm claims that it has found something, it has to be extreme. It doesn't have to belong to this distribution. If your algorithm belongs to this distribution, if we cannot claim that it's not, if we cannot reject the null hypothesis, what does it mean? Your algorithm is not better than random. Okay, so this is just an example p-value application, and yeah, it may also, yeah, it's in edge detection, it's in image processing. So it has this finding, it's used in molecular biology. So p-value basically tells how different your observation is from some null distribution, how extreme it is. The smaller the p-value, the more extreme your sample is. Okay, so by just looking at its value, it may indicate something. And there's some, by rule of thumb, the p-value usually is, and I'm going to stop afterwards. These are some, this table shows, for example, if p-value is less than 0.01, we usually accept it as a significant value. Sometimes it's 0.05. But if your p-value is larger than 0.1, it means that it's too large, so it's not significant. So the things in between, the p-values between 0.01 and 0.1, it's like the in-between cases where it's too close to call. Okay, so that's it from me for today. So this concludes chapter 9. And as I said, I've also uploaded exercise solving session video that I had recorded last year on YouTube, the same playlist. So you will have 3 videos from today's lecture, two from today, and 1 this additional exercise solving session. All right, I will stop recording now.